Thanks for the introduction. So for the one who was there at the talk before, I'm going to do the same thing for BGP as I did for the IGP. It gets more complex. The scaling factors are like an order of magnitude more, right? And there are a lot of issues to be solved there. They are on their way currently at the IETF. Vendors are changing the way they are designing and forwarding information base in order to accommodate this. So what I will do today is to describe an evolution of the data plane in order to accommodate fast convergence upon the loss of reachability of a next stop tracking BGP path. Okay? This is called BGP PIC for prefix independent convergence. You will figure out why later. And then I will come to the core of the topic, which is BGP Add path, which is a draft being standardized for years now, but it's accelerating a lot because the requirements are there and the first implementations are being tested, etc. And BGP Add path is a way of advertising multiple paths towards the same destination over a given IBGP session. Okay? So what is first BGP PIC? Well, BGP PIC is a way to achieve sub-second data plane convergence upon the failure of a BGP next stop. So we have pre-installed next stop in the data plane, and upon the convergence of the IGP, so when you figure out in your IGP that you lost the next stop, you will be able, the forwarding information base will be able to switch over towards the alternate path in a time that does not scale with the number of impacted prefix. Okay? We're talking about convergence, not fast reroute. So it's not about transiently encapsulating traffic along a pre-established path to finally reconverge to the optimal path. No, it's about installing the post-convergence path right away in the router before the failure. So let's review the history of forwarding information bases in distributed router architecture. So in the past, we had flat FIPs. So what does a flat FIP mean? It means that the different routing daemons are feeding the routing information base in the control plane part of the router. So we have BGP that lets the router figure out that to reach a given external prefix, it needs to use a given next stop, right? And we have the IGP who's telling the router that to reach a given next stop, it should forward the traffic over a given outgoing interface, right? In the past, what the RIP daemon was doing is to resolve this recursion from the BGP prefix to the next stop and the next stop to the outgoing interface. And what was installed in the FIP was a direct mapping between a prefix and an outgoing interface, right? So the recursivity aspect of these prefixes is no longer apparent, does no longer appear in the forwarding information base. As a result, your shortest path towards a given next stop changes. The forwarding information base must be updated for all the prefixes that you reach through that next stop. So if the router here loses its shortest path towards a given next stop, it's not only a matter of changing the forwarding entry for that next stop. No, it's also about changing the forwarding entry for all the prefixes that are being reached through that next stop, right? From there, we can move to what we call a hierarchical FIB, where we no longer flatten the routing information base to be downloaded as a FIB, but that recursion is still apparent in the forwarding information base. So what it means is that at forwarding time in the data plane, when you do a lookup for a given destination IP, you will figure out not the outgoing interface to be used, but you will get the next stop. And then you do another lookup on the forward, it's pipeline, you do another lookup on the forwarding information base in order to figure out what is the outgoing interface for that next stop. Which means that when the IGP converges and subsequently the forwarding information base is updated for that next stop, all the prefixes that are tracked by the given next stop, whose outgoing interface information has been updated, are converged, right? Classic. This provides PIC core. So this provides the fact that independent of the number of prefixes that you reach towards a given, that you reach via a given next hop. Upon IGP convergence, you get the recovery of the traffic being tracked by these prefixes. This does not help you if you lose the next hop, right? It does not help you to switch over to an alternate BGP next hop. For this, we have described what we call a generalized forwarding information-based architecture, where instead of only finding this hierarchical dependency, what we have is we have our sets of prefixes, right, who no longer directly point to a next hop, but they point to what we call pass lists. A pass list is a combination of a set of primary next hops. It's more than one if you have a BGP multipass enabled, and a set of alternate next hops. Okay? These next hops themselves point towards a given IGP prefix. So it points towards the information that I described right earlier that tells you for which destination address inside your IGP you have to send your traffic to. From this adjacency, we have a pointer towards the outgoing interface that has to be used. So as an example, we receive a prefix P here on ASBR1. Prefix, there is no alternate pass, so the pass list for P is just ASBR1 on its own, which points to the IGP fed information on how to reach ASBR1, which is via the neighboring, the adjacency here, R4, which himself points to the information that the outgoing interface to reach R4 is the north interface. We have the same thing for prefix Z, but we receive the prefix on both ASBRs over there. The router picked, for whatever reason, ASBR2 as a primary next hop, right? It reruns its BGP decision process in order to figure out what would be its preferred next hop upon the loss of the primary one. It figures out that ASBR3 is its preferred next hop upon the loss of the primary one, and installs it in the backup next hop list. All the prefixes that have the same combination of primary next hop and backup next hop share the same pass list. So these pointers, if you have 10,000 prefixes having the same behavior from the point of view of R1, the pointers from these prefixes are going to share that information in the forwarding plane. Let's assume that we lose our primary. So the IGP will figure out that the next hop ASBR2, which is down, the IGP will have to remove this entry from the forwarding information base. ASBR2 is no longer reachable, so that entry must be removed. The generalized FIB contains back pointers towards the pass list that point to them, right? So upon the removal of that entry, the forwarding information base will backwalk that list of pointers towards these BGP pass lists and remove these entries. As a result, when the packet processing engine performs a lookup and finds an empty set of paths in the primary pass list, it moves to the backup next hop and hence forwards the traffic towards ASBR3. Okay? So this means that the bottleneck of the convergence there is no longer the number of prefixes that you are reaching via the next hop. No, it's the backwalking time. So it's the number of pass lists that you have to backwalk in order to remove the entries corresponding to that next hop, right? Which happens to be actually pretty fast. And we run simulations on some tier 1 ISPs to figure out what would be the number of these pass lists, and they are much smaller than the number of prefixes that are tracked. So there is really a gain in sharing these pass lists by the prefixes. And this is where the trick is. This is how you get a fast convergence, because it's only a matter of backwalking this list. So we instrumented a testbed. It was based on the CRS1, where we were basically originating 100K prefixes on ASY, and we were generating traffic towards a tenth of these, right? 1,000 loopbacks were configured on the ASBRs in order to in order to create artificially a huge number of pass lists. And then what we did is that we fail X2 and we look at how much time is required for here NY1 seeing traffic after the failure. So we fail X2 and we simply watch the clock. When is our traffic that we evenly scatter towards these prefixes? When is it that we actually see packet again on the line? Well, basically it was the router had installed BGP multipass entries, so half of the traffic was load balanced and was already flowing through the source of the network, right? So only half of the flows generated were actually impacted by X2. And this is what we have here. On the x-axis, we have the sets of flows that were sent, so we have a K of them, and each set corresponds to one of the loopbacks that have been described before. So we had every time as a primary next stop the router on the north, and as an alternate next stop the router on the south. But these were different loopbacks, and hence these pass lists had to be backwalked 100 K times. Yeah.
When did you do that test? I mean, because for some time there was only
the question is, when did you do that test? Because for some time there have been only one routing engines for the CRS, but now there are at least two, I believe. So if the tests are quite fresh, so maybe you could share which route engine you were using.
Okay, you should ask your vendor for that, but it was one of...
Well, I'm asking for a CRS1 routing engine, because you mentioned CRS1.
Yeah, it was on the...
Well, but
the one that was there when iOS 6R 3.5 was there. It's
3.5. Okay, so there was only one then. Thanks.
So what we see on this graph is the amount of milliseconds. Thanks for the question. The amount of milliseconds that after which we saw the traffic again. I freaked out at the beginning because it was like 150 milliseconds, but then after that we figured out that the techie had let an artificial delay of the reactivity of the IGP itself. So the IGP took 120, 130 milliseconds before actually acting the removal of the prefix from the forwarding information base. So when you take this IGP reactivity out of consideration, you actually find the backwalking time, which has been shown to be a matter of a few milliseconds. So this is not a futuristic proposal. This is actually supported by some vendor. And so BGP PIC, and if you want to have PIC in your network, well, it's just a matter of figuring out whether it's supported by a network. But it is already being shipped. So, yeah. Oh, this one is... This was in a...
So this scenario, was it for core or for edge?
This is edge, because we lose the BGP next stop. Okay, so it's not only a matter of finding a new way to reach the next stop, it's a matter of having the forwarding information base backwalk and remove this next stop. So this is the PIC edge behavior. PIC core, in order to analyze the PIC core behavior, you have to analyze the convergence time of your IGP. This will define the convergence time of PIC core. So, well, PIC makes the data plane convergence very fast if you have alternate paths to converge to, right? And the problem is that there are many cases where the routers only have one next stop upon the failure time. They will reconverge and discover with IBGP path hunting they will find another path, but there are many cases where they only know one at the failure time. Why? Well, the first reason is the policies that you configure in your network that will typically lead to a case where all the nodes in the network prefer one single next stop. So if you have one path, here the blue path with a local pref of 100, and all the other ones for the same prefix are being assigned a lower local pref, well, by default, this ASBR will not propagate its external path. So all the other nodes in the network will only know about the blue next stop, and so the PIC will starve. It will not be able to figure out that ASBR2 should be used. rod reflection hides pass too, right? If we have the same local pref, and so that these ASBR advertise their own pass over IBGP, if you have a rod reflector in the middle that picks one and advertises it downstream to the PE still has only one pass, even though there are two available at the border of the network. So there is this nice tweak called advertise best external, which will let a router advertise an eBGP pass over IBGP, even though it is not its best pass. So when ASBR2 prefers an IBGP LAN pass, if he figures out that he owns eBGP pass, he will still advertise it, even though if it's not installed, he will still advertise it to the rod reflectors. So that when the rod reflector next stop track upon the failure of one of the next stop, they will already be aware of this pass, and they will, instead of sending withdraws to the PEs, they will send the alternate pass right away, so that the convergence will happen when this guy will have switched to its own path. The problem is that with rod reflection, even if you even if you enable advertise best external, if the rod reflectors receive the two paths, they will still perform a decision, and they will end up advertising the same path towards the PE, right? So advertise best external works to push paths towards your rod reflector, towards your rod reflectors, but these rod reflectors are still going to hide the path from the PE. So this was the motivation for add path. It's the fact that in many cases, a router has only one single next stop towards a given destination. This led to the famous med oscillation case that happened years ago, where due to the fact that some nodes were not aware of the path with the lowest med towards some prefix, they were picking suboptimal paths, and this was leading to an oscillation where a network would never converge, right? And so the motivation for Daniel Walton and Henke Chen at Cisco at that time to use that path was to let these paths be forwarded, so that never you would pick a path that does not have the lowest met value, so that never you can enter dissociation among the routers. The problem is that this case happened a few times, but in order to get there, you have to make some crazy configuration in your network. You have to have a combination of a weird IBGP design with a combination of a weird IGP design. So in the end, it was not happening that often. But since then, a lot of new requirements have pushed the IETF community to keep on thinking about advertising multiple paths towards a single destination. First, there is PIC, the fast convergence in case of failure. The ability to load balance your traffic towards multiple next stops, because if you have equally preferred paths, it's a bit sad to not be able to take advantage of them just because you need to have rod reflection because for scaling reasons. Having an alternate path is also nice to have upon a planned maintenance. When you shut down a BGP session for maintenance reason, or you shut down an ASBR for maintenance reason, withdrawals are being sent. If there are routers in the network that do not know about the alternate path yet, even though you are in a planned maintenance case, you lose traffic, right? So if you are already aware of the alternate path upon the maintenance, well, you just shut the router, and it's a matter of applying the PIC behavior. Another typical case where add path finds a reason to be deployed is optimal load balancing. Rod reflector make IGP tiebreak decision in the BGP, in the set of rules applied by BGP from their own view. They do not advertise to the PE the path towards the closest next stop, right? So if the view of what is the shortest path inside the network from the rod reflector perspective has nothing to deal with the view of the PE to whom is advertising the path, you achieve suboptimal routing in your network, right? So basically, what is add path? It's just a standard that says an update is no longer an implicit withdrawal from the previous pass towards the NLRI. No, an update contains a pass identifier, and so when I send you a pass towards a given NLRI with a given identifier, it replaces the previous pass with that identifier so that I can send you multiple. So this is, the draft is well, pretty well advanced now, and it is a working group doc at in the IDR working group. So basically, what this draft enables is you do not change your IBGP topology, and you can install PIC state, load balance among multiple next stop, not care about maintenance anymore, pick the closest exit, and you can also, I will discuss that about later, you will reduce the amount of churn, the amount of stress that you will put on your customers' routers, because thanks to the fact that you have a better knowledge of what are your alternate paths, you will send much less transient updates to your neighbors. So it's a bit like you will increase the churn inside your network because you will advertise paths that you no longer advertise only the best paths. So there are times where you will send updates for paths that you do not even use, but with the effect of reducing your chattiness on your eBGP sessions. Why? Well, because simply, when you only know one path, depending on how your IBGP topology is defined, you might have multiple scenarios. So here I have a case where my blue path on the left is the preferred one. I have a second preferred path here on the right, the red path, and I have a third preferred path here, the black one in the middle. So what can happen if you do not have add path enabled in your network upon the failure of your primary? Well, if the PE does not know about the alternate path, he will remove the entry from its forwarding information base, so he will start blackholing the traffic. He will send a withdraw towards its customer because he no longer owns the path towards the destination. As a result, the customer will probably himself trigger a BGP decision process and move to another provider or move to another link to your network. Then he will finally receive during the IBGP pass hunting inside the network, he will finally receive the red pass and hence send a new update towards the customer, which will itself, if this new update is preferred over the alternate path that he found towards through a competitor, he will fall back to you, right? It can even become worse if ASBR3 itself is not aware of the second best path is in the network when he receives the withdraw for the first one. So he might transiently think that he is the best exit for that destination and propagate its path towards inside the network. So as a result, PE, not knowing about the red path, might first send an update towards the customer reflecting the use of this transient path to finally receive the path with the new highest local pref in the network and send the final update, right? If you have that path and that PE already knew about the red path, first he will not send the withdraw towards the customer because he can send the update right away reflecting the red path. And if the attributes of that path have not changed, actually you may remain silent, right? If the set of attributes of the path, as the local pref is local, right? So you do not talk about your local pref on your eBGP sessions. So basically, if the attributes that I have advertised for that path over your eBGP session have not changed, the customer will not even see that there was a failure in your network. So instead of sending 1, 2, 3 updates and sometimes a withdrawal transiently, you will either send the definitive update or stay silent. Okay. In the internet route case, due to the set of communities that are always different among your paths, you most of the time end up sending an update, right? But the most important stuff is that you do not trigger a convergence in the customer network for nothing. But now the big question is what to send. So the draft defines a way to advertise multiple paths towards your IBGP neighbors. It does not tell you which path to pick, right? And the issue that we've been facing is that well, I've been telling you this huge amount of applications for add pass, but then when you have the engineer think about his own application, the critical one for him, it will lead to a decision on which path should be advertised, right? So if what you are facing is med oscillation, you will make a propagation, you will want to implement a propagation strategy that will never let a router not be aware of the path with the lowest med towards a given neighboring AS, right? Because when you do that, you never pick path with the higher med, and hence you cannot enter in an oscillation. If the goal is to simply have fast convergence, well, all you want to do is to advertise your second best path, to have the rod reflector advertise their second best path towards the PE, right? No need to advertise all the paths with the lowest net. So advertising 2 paths over this session is over all your sessions is already sufficient for PIC. If the goal is load balancing, well, you have to advertise as many paths as the number of paths you would like to load balance to, right? So here it becomes more like a add n paths where you would configure n. If the goal is to have planned maintenance, be it less, then you only need to find, based on the topology, you only need to find a strategy that will never let a router be starving of a path, although it's available, one is available at the border of the network, right? If the goal is to stay silent upon the failures within your network and not disclose them to your customers, then the strategy will favor the dissemination of the post-convergence path. So we were discussing with ISPs, and they were like interested in that path, but not knowing the amount of memory that it would take, what is the recommended selection strategy. It was a bit blurry from the vendor side on what would be implemented. So we gathered up with some vendors and some ISPs in order to make a list of the proposal from engineers, from the academia, from the vendors themselves, and figure out which, if there is not one that would fit them all, or a restricted set of strategies that would be sufficient in order to meet the largest number of requirements. So for that, we have a working group doc at the IDR working group at the IETF that is called a draft IETF IDR at pass guidelines. So it reviews all the main decision strategy and tries to explain what they do and analyze what you get at which cost based on the characteristics of your network. A lot of modes have been proposed. I'm receiving proposals of them on a regular basis. We're trying to get rid of most of them because every time it's a new implementation, it's new testing, and to be honest, if some vendor decides to take one mode and the other decides to take another, etc., well, sometimes you're not quite sure what is the end result in a multi-vendor network. So here comes the main lists that of the modes that still survive kind of in the analysis part. So the first mode is all pass. Quite simple. The rod reflector basically picks all the paths that it knows about, and it propagates over an IBGP session all the paths but the ones that it received over that IBGP session, to make it short. For the vendor, it's cool because it's the easiest decision process algorithm you could think about, right? It's like, I pick all the paths that I know. I like this mode if you have a box that is just dedicated at collecting paths, because if you have this box establish and add all paths enabled towards the ASBR, you will get all the paths that are available at the border of your network with a simple standard BGP session, right? So it's like you will use the capabilities of the update packing of your routers that are there to do routing in order to do monitoring. So it's a quite easy way of getting all the paths at the border of your network with an already deployed on an already deployed network. Depending on the number of paths that are available at the border of your network for a given destination, it can become a memory monster. Control plane memory, right? I mean, it is not because you receive 15 paths towards the same destination in your control plane that you will install the 15 of them, right? So we're talking control plane there. But still, having these being constantly updated might start to become a bit concerning in large ISPs where a lot of paths towards the same destinations are received from transit, peers, and customers. Please, if you test that path from one of your vendors, check for this. If you have in your network a hierarchy of rod reflection, a router at the first level, a rod reflector at the first level of the hierarchy might receive copies of different paths, from its higher layer, right? Check from your vendor if the implementation does not consider these four as different and does not end up advertising for paths towards the PE. Yes?
Would that be due to the identifier would this be due to the identifier that it would be received from the two route reflectors with different identifiers and considered different?
Exactly. It's basically the developer just not paying attention to the actual equality among the paths received from the different rod reflectors and advertise them.
What would happen in freaky situations where we would have multi-vendor rod reflectors?
But that's okay. I mean, you just need to check for this to not happen. And I mean, the identifier only in the standard only has a session meaning, right? The identifier for a given path is not global through your network, right? So basically, so
the second one in the hierarchy has to make sure that he does not include the identifier into its global view when it looks at all four of them?
When it checks for the equality of the path that it receives from the rod reflectors, yes. The second mode, which is the most intuitive one, is add n pass. So you basically you configure n and you let your rod reflectors advertise their n best path. So it's a mode that is equivalent to, I do not say that it should be implemented that way, but it's equivalent to, first, you get your entire RIB, you compute your BGP, you run your BGP decision process, it gives you your best path, you take it out of consideration, and you do that again. You do that until you no longer have paths or you reach n and gives you the set of paths to advertise on the session, right? Usually we consider next stop disjoint paths because the main driver for this mode is PIC, right? And if you advertise the same path, well, two different paths towards the same through the same next stop, if the next stop fails, well, the backwalking mode will remove both your primary and your backup path, so it does not make any sense. So we recommend to, when you take out one path, to also take out the paths that have the same next stop. It's the mode that is basically covering the most practical use cases, right? You set n to 2, you have support for PIC in the control. You have a control plane that can feed PIC in the data plane. If you want to get load, if the goal is load balancing, well, you configure n to the number of next stop over which you want to load balance your traffic. If you're a bit afraid of your memory consumption in the control plane, well, you have a knob in order to reduce the chattiness of that path in there. It does not, in theory, it does not solve med oscillations. So you give me an IBGP topology that oscillates with med, right? You give me the value of n. I will tell you, well, if you add these sessions to these eBGP sessions to these customers, you will get back to your oscillation, right? So in theory, advertising a fixed additional amount of paths will not prevent from oscillations from happening during the evolution of your network. But seriously, I mean, I'm not quite sure anyone cares anymore about med oscillations because, well, they're just not happening anymore because people are now paying attention to how they are deploying their IBGP topology with respect to how they are, designing their IGP. I'm a bit concerned if developers implement the decision process as n times running the decision process. If that part happens to not be the bottleneck of the entire BGP selection process, that's okay. If in some implementation it tends to be the case, there are ways of not doing that as naively. So we will see what happens. Another mode is called AS wide best pass, where the idea is to never let a rod reflector hide a pass that one of its ASBRs could have picked. So basically, it means what? It means applying the local preference rule, applying the AS pass length rule if it's not ignored, applying the MED, and then stop. When you are done with the MED rule, so when you have skimmed all the paths that do not have the lowest MED from each of your neighboring AS, you stop. You do not apply the IGP tiebreak. As a result, what you will do is advertise towards your PE all the paths that should be tiebreak based on the IGP. And as a result, the PE will actually pick the closest next stop. And so you will not, due to the way you define your rod reflection topology, you will not end up using way suboptimal paths across your network. So with this mode, the router does not make local decision for its PEs. The complexity of the decision process is lower than not running at pass because you stop earlier on. If you load balance starting from there, so if you enable BGP multipass to load balance among all the either ECMP or even not ECMP next stops, then you get all you need in order to do BGP multipass in the data plane. It provides MED oscillation avoidance because if you look at the mode, you will figure out that never you advertise a pass, never you hide a pass with a non-lowest MED. So everyone knows about the pass with the best MED towards each of the neighboring AS, and hence you cannot get into this oscillation. The only problem is that it does not fit PIC, which to me is the most critical feature for that drives the standardization of that pass, for the simple reason that as the definition of that mode is to apply the rules up to the MED and then stop, well, if at the first rule you get one pass, voila, you will advertise one pass. Okay, so basically, do not deploy AS-wide best pass, or do not push the vendor to deploy AS-wide best pass if your primary goal is to obtain fast convergence in the network.
Not really related to the slide anymore, the end times decision process. Wouldn't I, when I run a BGP decision process, end up in a list somehow anyways, ordered by whatever I want to decide? I mean, why would I have a need to run the decision process multiple times if I could run it once, have my list with my preferred, and then pick my end time stop from the list?
Because the decision process does not apply a transit. The decision process of BGP is not transitive. So the fact that you prefer A over B and B over C
does not mean that I prefer A over C.
Not knowing about B, you prefer A over C. And due to that, you have to pick and remove, and there is not an ordered list of preferred paths, and it's due to the MED rule. Right? So if you ignore MED, well, then you could do that. If you don't ignore MED, as the relationship, the preference from a path over another is not a transitive relation, you cannot do that. Because removing a path from consideration might change the preference between two other paths. Right? That's actually what has caused all the divergence cases in BGP. It's always due to that. It's due to the fact that this rule, the BGP decision process, does not implement a transitive relation among the different paths that it has.
Thanks.
So the last one I will talk about is called neighbor AS group best. It was historically the first one proposed. It was typically defined to avoid MED oscillations. And what it says is that you split your ribbon in the sets of paths based on the neighboring AS from which you receive these paths. So basically, I will make a first set of the set of paths that I receive from AS1, a set of the set of paths that I receive from AS2, etc. I apply my decision process on each set separately, and this gives me the best path towards each of my neighboring AS. As a result, never a router is not aware of these paths, and as a result, he will never push in the IBGP topology a path that does not have the best med for that neighboring AS, and hence these associations will not occur. If you receive a path towards the same destination from two different neighboring ASs, you can feed PIC with that mode, right? As it advertises the best for each neighboring AS, well, you will install as a primary your preferred one through one AS, and as a secondary, the preferred one to the other AS. The problem is that sometimes you receive a prefix only from one of your neighboring ASs, and sometimes this has nothing to do with your post-convergence path. There are many, many cases where when I lose a link with my main transit, after convergence, I will use my second link with that main transit. So if you have, for example, you are a national ISP with, the international version of the same company, and this is always the one that you are supposed to prefer, right? And then you have a competitor as a second of this global company as a second provider. Typically, your policy will drive your decision process to pick as best a path towards your main provider, and after convergence, it will be still towards the main provider. That mode will give you the best path through your main provider and the best path through the provider that you only have there in order to reach the rest of the world when you completely lose your primary provider. So the tedious job that we've been doing is to list all of them, make an analysis of the sets of what do you get at which cost, etc., etc. I skipped two of them because I'm already late. So basically, what we can see is that first, except for Add-N, you can always find a case where these modes are going to be as memory consuming as advertising them all, right? So except for Add-N, which provides you a bound to the number of paths that you will have to maintain in your routing information base, which is basically the number of paths that you have to, the number of prefixes that you hold times the number of times n times the number of IBGP sessions that you have. This gives you your upper bound for the memory consumption on a given routers. Well, the other ones don't know. I cannot tell you in advance. With such a simple formula. I have to have you send me a show IP BGP all on your ASBRs, or if you use advertised best external only on your rod reflectors, I have to look at your IGP topology, and only at that time I can tell you what is the memory consumption in your routers based on the different modes. With Add-N, I can tell you right now. I can give you the simple formula to get your feeling on what will be your memory consumption in your network. Med oscillation avoidance is actually provided by almost all of them but N, right? And this really motivates me to try and get rid of the ones that have been specifically defined for so, because they're really bad at supporting PIC, which is to me the most preferable, the most important use case for AdPass, right? So these modes have been designed in order to reach med oscillation avoidance, but the main motivation to implement and deploy AdPass is about peak and load balancing and optimal routing, which these guys are not good at providing. So I would recommend to not put a high priority on these modes. I will skip this because I'm super late. So what remains when we have skimmed these and the ones that are defined to avoid med oscillations? Well, we have add all and we have add n. The nice fact with add n is that it's bounded. In theory, it does not necessarily give to the PE the path towards the closest next stop, but well, by increasing n, you end up getting there, as in many cases, the rod reflector is kind of close to the PE. Well, you do not need to set n to 10 to get optimal routing. But in theory, you cannot find a specific number that will ensure that you have optimal routing through your network. So the recommendation that we are currently, if you disagree with that, it's still time to go shout at the IETF. The draft is still, it's a working group doc, and we're still taking the comments from the audience into consideration. This draft is living. But the current recommendation is to have add n as a must. So someone implementing add pass must support add n pass. It must set the default to 2. We decided to do that in order for not having an operator enable add pass and have a crazy vendor make the default to a large number or to all, and have, as a result, the PE be clogged with a number of pass. So add n must be supported. As soon as the operator turns it on and does not specify n, it must be 2. Okay? N must be configurable because we know that there are ISPs who want this to load balance among 4, 8, 16 links. So if he wants to get there, well, we recommend this to be configurable, and we leave an option to not limit the number of paths, which turns to be leaving an option to support add all. I'm a bit in disagreement with my co-authors there, but as an optional mode, don't ask me why. I mean, AS white best and some of its variants are, I mean, because there are 6 modes here on the talk, but on the draft it's like each of them has some variants. AS white is still left as optional, and all the others are, if the vendor wants to support them, okay, but we do not feel that, based on what we've been discussing for months now, we do not feel that there is a real push for them. From a deployment point of view, well, if your PE comes from a vendor that will not support add pass, it's useless, right? If the rod reflector speaks add pass and the PE doesn't, well, you can do everything you want. You will not get PIC working in your network, right? So, as compared to Robert Watsuk's proposal of diverse paths where you establish multiple sessions in parallel, this you can do with a PE that does not know about anything about PIC, right? I think that if we find that many vendors are present at the edge do not support that path, what we will do is we will keep on that path and we will implement a wrap-up in order to turn that path in a diverse path signaling mechanism, so that we will have this PE take advantage of that path still. If you do not have encapsulation from ingress to egress in your network, watch out, right? Because it's not because your ingress is going to pick, you know, its policy, the best path with its policy, that the rod reflectors in the middle or the other nodes in the middle are not going to contradict that choice, right? So if you allow that amount of flexibility thanks to that path for the decision of forwarding traffic towards a given destination, well, you have to watch out that the intermediate nodes are not going to fall back to what you would get if you would not have that path. There are some implementation of prefix-independent convergence. I'm out of time, sorry. There are some implementation of prefix-independent convergence that are a bit naive and that might lead to transient forwarding loop. So you fall back to the alternate next hop, and if the PIC implementation of that alternate next hop is naive, it might not figure out that he receives traffic that is deflected towards him and send the traffic back to the primary next hop, which has failed, right? So watch out that your vendor takes that into consideration when you deploy some technology like that. We have a tool, so if you're interested, we have a tool that, based on your IGP config, a BGP feed and the IGP topology will tell you with which mode, what will be the amount of paths that you will be advertising to your network, and well, basically what you will get at which cost. I think I'm done, so I will just take one question or two if there are any.
Just a short one.
Do you know if there are, if it is road mapped for Cisco or Juniper?
On the way.
See your point. I mean, it's being implemented, right? I mean, it's like there is definitely. Huh? Yeah. I mean, it is. There is clearly a motivation from some of them to go there. I mean, I'm not sales. I mean, I'm working with them. I'm not doing marketing with them. Please go ask them. Do not put me in that situation to go leak their internals to you. I mean, they're there in the room, right? I mean, go ask them. or in the hall.
So thank you very much for the presentation.
Thanks.
And yes.